Hello everyone. If you are familiar with my channel, you may know that all of the projects I presented up until this point have either targeted the TI-84 graphing calculator or my Mac laptop. Now, in both cases, I've actually been shielded from the realities of working closely to hardware. On my Mac, there's the operating system, macOS, and it handles all hardware interaction. And on the TI-84, there are a lot of open source libraries I use which kind of abstract away the realities of the calculator. Anyway, so for this video, I thought I'd embark on kind of an ambitious project which would force me to learn about real hardware concepts like interrupt handlers and virtual memory and multitasking. So I ultimately decided to write my own 32-bit kernel for the x86 family of chips. It took me about 2 months and it is by no means finished, but I feel I've reached a pretty good stopping point for now and could make a pretty interesting vlog about the project. So with that, I guess we could just jump into it. Okay, so first things first, my operating system is called FernOS, like the plant. That was an arbitrary choice. But anyway, if you were to download my Git project, you would see a file tree like this, where there are a bunch of folders in the source directory. Each folder represents like one module, one group of code that's related in some way. They all follow this weird prefix naming scheme that I'll explain a little later, not right now. But just to get things going, what we really care about to start with is this file, main.c. So when the kernel starts up, it's going to initialize a bunch of structures, configure the memory correctly, and then it's going to create one single process with one thread, and it's going to schedule that thread and just kind of kick off the scheduler. So what that means is after initialization time, this function basically gets entered. And when this function returns, when the root process exits, the entire system stops. So right now, our function does nothing except return success. So if we were to run this program, make qemu.bin, let's see what happens. So we get system exited with status 0. Great. So the operating system stopped because the root process exited. Nice. So as you may have just seen, FernOS doesn't have like a graphics driver yet. All output just has to be printed to a text terminal. That's really the only way to give information to the end user. Now, if we wanted to print out information to the terminal ourselves, we don't actually have access to the terminal directly from a user process. We have to use something called a syscall. The idea here is that when user code is running, it does not have permission and access to kind of the full system. Only the kernel has permission to do whatever it wants, really. So what we do is we use something called a syscall, which kind of goes through this hardware pathway to switch from user mode to kernel mode and execute some sort of operation we want done. So a syscall is us kind of politely asking the operating system to do something that we normally wouldn't be able to do. For example, printing to the terminal. So if we go into syscall.h, we can see a giant list of system calls we have access to. Later in this video, we'll go through each one and how to use each one and why each one exists. But for now, we might as well just use the simplest one, which is sc term put s. So let's try it out. So sc term put s. Hello from user main. So let's see what this does. Look at that. hello from user main. So we have successfully printed to the terminal. All right, so thus far in this video, I've used the term thread already, and I wanted to just kind of like give an explanation of what a thread is for those who might not be familiar, and kind of lead us into the next category of system calls. So what is a thread? Is a thread. So in my operating system, a thread is kind of like, you could kind of just think of it as one sequential path of instructions that's taken by the operating system. So for example, this is a thread right here. We start with one thread. What it does is it prints out hello from user main, and then it exits the system. To demonstrate multiple threads, which is something we can do in FernOS, let's kind of augment this program a little bit. So instead of exiting the system, we're actually just going to run forever. Thread sleep 8. All right, let's run this and see what happens. All right, so now our system never exits, and this same message just keeps getting printed out over and over again. But now, I mean, with one thread, our entire system is consumed by this while loop. It would be nice if we could have something else going on at the same time, which we can. So what we could do is we could make another function. I could call it other path. And actually, let's just take this. Okay, so now we have another function that seemingly does the same thing. While loop prints out a message and just does that repeatedly over and over again. Can we run these things both at the same time, even though both of them run forever, if that makes sense? Like none of them really give up control, it seems. How can we still run them at the same time? And the answer is yes. So we could have a FernOS error. So from here on out, most system calls are going to return an error. So that's what this type is, FernOS error T. So we can do error equals SC thread spawn null other path null, and we could say if this fails, return proc es failure. All right, so let's see what happens now. Okay, let's see what happens. Yeah, so now the print statements are interleaved, which is pretty cool because the system we're working on only has one core, which means no two instructions can actually execute at the same time. What's really going on here is what the operating system is doing. It's saying, okay, I have two threads. I'm going to run a little bit of this thread, and then at a certain point, I'm going to switch to the next thread, and then I'm going to switch back, and I'm going to kind of do the zigzag pattern between these two workers. And the result are these interleaved print statements. So that's kind of like an initial example of threads on FernOS. Anyway, this example is extremely simple. Now, let's kind of maybe jazz things up a little bit. One thing we can do, or one thing that's important to note, is that all threads have an ID value between 0 and 31. So for example, this TID argument, or thread ID, we gave null, but one thing we can actually do, I'll say TID, we can actually get the ID of the thread when we create it. So we can say, this is like the format version of print. We can say thread spawned with ID %u. And we'll give it the thread ID. So let's see, this should give us the ID of the thread we just created. There, so we spawned a thread with ID 1. Why is that important? Because we can use the thread ID later to kind of synchronize, for example, right? So let's say this. Let's say we actually didn't want to do this loop right away. Let's say we actually wanted to spawn some thread for the thread to do some sort of work we don't know about. And then when it completes, then we want to enter this loop, right? We want to pause our thread until the other thread completes. That is something we can do. So we can do air equals sc thread join. And then what we do, this is kind of interesting, but thread IDs are from 0 to 31. This way, with a 32-bit integer, we can, each bit can represent a single thread, right? So if we want to join, the process of waiting on another thread to complete is called joining. So if we want to join on just the thread we created, what we would do is we would bit shift 1 by the thread ID. And then we don't need that. And we don't need that. And same thing, we could say if this doesn't succeed, we'll print some sort of error. So now, let's see what happens here. So now we spawn our thread, we get the thread spawned message, and we get all these hello from other paths. We never get the hello from main path because our other path never actually exits. So let's see what happens when we actually exit our other path. And how could we do that? What we could do is we could say, this is what we'll do. We'll say, other path is doing work. And we could thread sleep for a little bit. I don't know, 20 ticks. And then we will return some random value. We'll say void start 1. Now let's see what happens. All right, so our other thread's doing some work. It finished, and we get back to the hello from user main loop because we successfully joined. Another feature of joining, which you might really have alluded to, or really of threads in general, is that not only do we have this void star arg, but we also return a value. So for example, when we spawn our thread, we can actually give it a value, kind of like an argument. Like maybe we want to give it void star 1. And we can say, other path is doing work on argument. And what we will do is we will print out the value of the argument we were given. What's wrong? Oh. Okay. And at the very end, what we could do is we could return, we could take the argument, convert it to an integer, and maybe return it plus 5. So let's see what happens now. Well, actually, okay, this is what we'll do. So now what we're going to do is we not only want the main thread to wait until the other path completes, but we also want to get the return value of the other thread that it exits with. So we got to do some funky casting here, but don't worry, it's not that complex. So we get the red value, and we can say joined thread with return value %u red val. So if all goes well, we would expect this to print out with 5 plus the argument we gave it, which was 1. So we should see join thread with return value 6. Look at that, it worked. And we get back to our main loop. The nice part about this feature right here with the 1 bit shifted is right now it doesn't really matter because we're waiting on just one thread. But it would be more common that we're waiting on many threads. So now, for example, what we could do, let's see about this. So what we could do actually is we could say const uint32t workers equals, I don't know, 5. And I equals 0. I is less than workers. I plus plus. All right, so now instead of spawning just one worker, we're going to spawn 5. And maybe we'll pass in I as the argument. So each thread is going to run the same piece of code, but each thread is going to run the same piece of code, but now with a different argument. And then down here, what we're going to do is we are going to wait for all of them to finish before we continue on to our original loop. So now what we're going to do is we're going to have another loop called uint32t I equals 0. I is less than workers. I plus plus. So we're going to take this whole thing. We can take this out. And so now this is kind of the part I was alluding to earlier. So now we want to wait on any thread, really, not just one. And the way we do that is we would add a 1 bit for every thread we'd want to wait on. If we want to wait on thread with ID 2, bit number 2 would be a 1. If we want to wait on thread 2 and 3, bits 2 and 3 would both be flipped to 1. Now, if we just want to wait on any thread, what we can do is we can do full join vector, which is really just all ones. So basically, any thread exits, we will join on it. Okay, so let's see. We have the ret value, and we can also retrieve the ID of the thread which exited. Well, do we even want that? Yeah, this is what we'll do. %u spawned with ID tid. And then here we can do sc term put format s, and we can say thread with ID %u joined with retval %u retval. Let's delete this. All right, let's see what happens now. And just because we're going to look at the output for a while, we're going to make this a little bit slower. Okay. All right, so thread 0 spawned with ID 1, thread 1 spawned with ID 2. So we're doing some work. Here we have thread ID joined with, uh-oh, that ret val is wrong. Why is that so high? Oh, whoops. I need to print out the ID also. Why is that? Okay, now let's try it out. And let's just take this out because it was annoying. Make qemu.bin. All right, so now We have thread 0 spawned with ID 1, thread 1 spawned with ID 2, okay? We have thread with ID 1 joined with ret value 5. That makes sense because it was given argument 0. 0 plus 5 is 5. Thread with ID 2 was given argument 1. 1 plus 5 is 6. So basically, this is just a demonstration of how we can spawn a bunch of threads and then wait for them all to finish. And kind of wait on any arbitrary thread to return a value. Okay, for the final part of this video on threads, I wanted to talk about something called a mutex. A mutex is a structure that is implemented a little bit in user space and a little bit in kernel space. It relies on kind of like a nuanced system call. Instead of explaining what that system call does, I'd rather just show you how to use a mutex and kind of explain the intuition behind what a mutex is. So a mutex stands for, or is short for, mutual exclusion. It can be thought of as, you can kind of think of it as like a hall pass. Like if you're in school and maybe you need to go to your locker or to the bathroom in the middle of class, you take the hall pass, you can go. And then if you're another student and you want to go into the hall, you have to wait until the original student comes back, right? No two students can be in the hall at once. That's kind of like an analogy that describes this idea of mutual exclusion. And why is that important, right? So I've kind of modified our program a lot since the last clip, but the idea here is now we have our other path thread still, but now we have this kind of global state, and the state has a buffer and an index. And the idea is that the buffer is going to start with the 0th index being A, or I'm sorry, the 0th slot being A, and then the index field being 0. And what we want each worker to do is to read the value of index, increment it, so shift over a slot, and write the next alphabetical character to that slot. So the first slot is A, a thread's going to come in, it's going to read A, it's going to advance to the next slot and write B, so on, right? So let's see this in action. So we have, I've kind of written up that code real fast, and I added this sleep statement, just you'll see why in a second. So we get the character, we increase the index, we determine what the next character should be, and we write that to the slot we are on. And we have one worker here, so let's run this. Make qemu.bin. Okay, so we have A, B, C, D, E, F, which makes sense because the loop runs 5 times and A is initially in the buffer. So A starts and then we had 5 more characters. So that looks good, right? Oh, and ignore these print statements for now. I'm gonna explain them in a second. So now let's try 2 workers now and see what happens. Okay, with 2 workers, we just get A, which is kind of confusing. Like we would expect 2 workers, 2 threads, both iterate 5 times. So we would expect 10 characters to be added to our buffer, but we just get A. You know, why is that the case? And this is where like the hall pass analogy becomes important. The idea here is that the operating system, manages these different threads. And the operating system jumps between the threads at random times. The operating system knows nothing of what the thread is actually doing. And it has no idea that certain operations that threads are doing shouldn't be kind of shared between threads, if that makes sense. Like, this section that I call the critical section is kind of like the hall, it's kind of like the bathroom, like only one student can go at once, right? So we need a way of telling the operating system, look, like if one thread is doing these operations, another thread shouldn't be able to do them, right? The reason why we got A last time around, just A and not the 10 characters appended, is probably because one thread came in and incremented the index. The next thread came in and incremented the index again before the first thread could even write its character to the buffer. So what happens is that the first slot holds A, the next slot holds the null terminator, but this next slot never gets written to, it gets skipped over, and then when we print out the whole string, it just prints A, and then it gets to the null terminator, and it's like, oh, the string's over, right? So the idea here is that this area really can only hold one thread at once, okay? And that is where a mutex comes in. Okay, so now let's actually use the mutex structure and see it in action here. So let's do static mutex t mute, and then down here we can do air equals init mutex and mute, and then if this doesn't equal success, we will fail. Okay. And before we run this, okay, so now before we enter the critical section, we should do mute lock and mute. And when we exit the critical section, we can do mute unlock. This is like the hall pass kind of. And then as a final touch, I should note that my mutex implementation is not fair, which means it doesn't really keep track of which threads have been waiting for longest. So anyway, that's kind of a more detailed topic that we don't really need to talk about in this video. But the point is I'm adding this extra sleep statement just to help out with the example. So let's see what happens now. Sweet, so we get our 10 characters. And if we look at the print statements, we see that thread 1 doesn't enter the critical section until thread 0 has exited. And thread 0 doesn't enter the critical section until thread 1 has exited. There's never a situation where, there are two entering print statements right after the other, or there are two exiting prints one after the other, right? So this kind of proves that the mutual exclusion is kind of working, and we could even beef it up a bit and add more workers. Like if we had 5 workers, let's see what would happen. Sweet, that looks good. Okay. Now, just like thread, there's another term I've thrown around a lot in this video with little explanation, and that is process. The idea of a process is perhaps even more fundamental than threads, but I decided to wait till the end to talk about processes because I think they're a little bit harder to understand at times. Basically, to talk about processes, we would first need to talk about something called virtual memory. What virtual memory is a feature that is supported by the x86 chips, and I assume like most modern chips. The idea is that, let's say I have a pointer like uint8t star pointer, and this is going to equal OX 2000, for example, right? And I say, okay, I want to go to address OX 2000, and I want to write 5. Now, the idea of virtual memory is that the address that is baked into the machine code is not actually the memory address that is really used. When virtual memory is turned on, what actually happens is OX 2000 is referenced in the machine code, and then the hardware goes to something called a page table. And the page table looks up OX2000 and spits out a physical address. For example, maybe OX2000 really maps to OX40,000 in physical space. So when I say star pointer equals 5, I'm actually writing to this address. This has like many benefits. I won't really go into it in too much detail, partly because I am not even that versed in virtual memory, but I did set it up in my operating system. So I thought I'd explain it to kind of give a lead-in to processes and how processes work. So why it's important that we understand this idea of virtual memory for understanding processes is a process is really just a memory space plus a bunch of threads. And by memory space, I really mean a bunch of page tables. So for example, if I'm in process A, maybe in process A, OX2000 goes to OX4000 or 40,000. But in process B, the same instruction writing to the seemingly same place in memory actually writes to OX80,000, which is a different place in memory. So this is kind of confusing. Like, how do I go about getting this process A and process B? Do I need to know what their physical addresses are and what their page tables are? How do I work with them? This seems kind of confusing. And you are right to be confused because this is very confusing. But basically, my operating system offers up a system call called fork, which is similar to the system call fork you might see in Linux or Unix-like operating systems. So, for example, this is how it's going to work. I'm going to take a FernOS error, and I'm going to say error equals, and I'm going to also have a proc ID cpid, and the error is going to be sc proc fork and cpid. Okay, and let's see what happens here. And what I'm going to do is I am going to have while1 right here, and I'm going to say if error doesn't equal FOS success, we will just return immediately proc EC failure or ES failure. And what I'm going to do is I am going to, what should I do? I'll say value of cpid %u. So let's see what this does. Okay. So this is kind of interesting. We actually got two print statements or two outputs, but if we go to the code, we only have one print statement, right? So what really happened here? Fork, kind of confusingly, what it does is it kind of returns twice in a way. What fork really does is it takes the current memory space, which I could say page tables, and copies them with new underlying physical pages. So what does that mean? That means and then what it does is it schedules the main thread of this new process. So the idea here is that in the compiled code, the address of cpid will be the same in both the original process and the forked process. But there actually will be two copies of this variable and all the variables in physical memory. And we could kind of prove that, well, we kind of just did, because when we printed out CPID, we actually got two different values. We got 1 and 256. So let's like dig into this a little more. I know it's a little bit confusing, but for example, the way you would really use fork is what you say is, okay, I know if I am in the process which was created, the value of CPID will equal max prox, which is an invalid, which will never be the value of a valid ID, right? And then otherwise, so we could say while one, and here we could say term, sc term, put s, hello from child. And then down here, we can say sc term put s hello from parent. So let's see if this works out. Nice. So here's like a very basic example of spawning a process. So you may have remembered from about 5 minutes ago the example where we had multiple threads working on some sort of shared state, and the threads could kind of interact with each other in this way. With processes, this isn't really a luxury we have available. For example, if I had an integer, shared number, and I wanted process A to write to the shared number and then process B to read from it, that could not happen, at least initially, because shared number, while shared number has the same virtual address in both processes, under the hood, it'll have two different physical addresses. When process A writes to the shared number, it might go to OX 60,000. When process B writes to shared number, it might go to OX, 90,000, right? So anyway, that's an intro to a family of strategies known as IPC, which stands for Inter-Process Communication. Examples of inter-process communication on Linux include signals, pipes, and shared memory. In FernOS, right now, there's only kind of a version of signals. So that is what the final part of this video will be about, communicating between processes using signals. Okay, so what is a signal on FernOS? It's a little bit different than maybe Linux or Unix, but kind of similar in some ways. So the idea is that every process every process has two 32-bit vectors. Or I'll just say I'll say vectors, why not? And the vectors are, we could call them sig allow and just sig. So the idea here is that there exist 32 different signal types, numbered 0 to 31 inclusively. Okay? And what happens is that a process can send a signal to another process, and a process can also receive a signal, right? So when a process receives a signal, it is cross-referenced with the sig allow vector. What this means is that by default, the sig allow vector is all zeros, which means no signals are allowed. And if a process receives any type of signal whatsoever, it will it will immediately exit. So to give an example, we could do something like this. We could take our child process and we could say forever, let's print hello from child and sleep. I don't know, 10. And then what we're going to do is we could say thread sleep, I don't know, 40. We'll sleep for a long time. And then we'll say st term put s, signaling child. And then what do? We do sc signal, and we give it the ID. So remember, in the parent process, which is the process that spawns the new process. So, sorry, in the original process, I should say, we have access to the ID of the process we spawned. So we can signal cpid, and we give it an ID of a signal we want to give it. So let's say 6. And you know what? We're going to do one thing really fast up here that I'm going to explain later. Signal allow full sig back. Okay, I'll explain that later. So let's see what happens. So what's supposed to happen, we're going to spawn the child. It's going to print out a bunch of stuff, and it should exit abruptly when the parent comes in and signals it with a signal that the child does not allow. So let's see what happens. From child, signaling child. So look, we signaled the child and then the print stopped, which kind of tells us that the child process exited in some way, right? Okay, what next? So, okay. If, and we could say if a signal is allowed, so if a bit is set in the sig allow vector, what will happen is that the corresponding bit in the sig vector is set. Okay. Then we could say in the future, or currently we can say, if any threads are waiting on a specific signal, I'll say on the received signal, in the future, okay, if any threads are waiting on the received signal, wake those threads up. Okay, so, or I'm sorry, wake one of those threads up, not all of them. Okay, so let's think about this. Let's see this in action here. So maybe what we could do is instead of signaling, let's think about this. Instead of signaling from the parent to the child, let's now instead signal from the child to the parent. So we'll say sc signal and we'll do sc threads. We'll sleep a bunch so we can kind of see the effect. We'll do 40 again. And we're going to signal FOS max prox 5. Okay, so what's going on here? If we provide, I should have said this earlier, but processes follow like a tree-like structure. When a process spawns, when a process forks another process, it creates what's known as like a child. And that child is kind of like a leaf on a tree whose root is the parent, or whose kind of one of its inner nodes is the parent process. So when I do signal and I give it FOS max prox, which is an invalid ID, what it'll do is it will go instead to the parent of my process, the parent of the spawned process. So I don't need to know the specific ID of the parent to signal it. I can just give it FOS max procs and it'll infer it. So, okay. So we're gonna wait for 40 ticks and signal 5. And for the parent, what do we wanna do? Let's do, we're gonna take this out for now. And we're gonna do sc signal allow. And similar to threads with adjoining, we are going to allow the 5th signal bit. And then what we're going to do is we're going to say air equals, we don't need to check for error. We trust that it's going to work. Signal wait. And we are going to wait on signal 1 through 5. Or, no, I'm sorry. We're going to wait on signal 5. And then at the end, this is what I'll say. I will send, or I will print out after waiting signal received from child, and up here before I send it I'll print out signaling parent. All right, let's see what this does. So we should see signaling parent, and then the parent process should wake up, and this should all happen after a little bit of a pause because of this sleep statement. All right, hello from parent, signaling parent, signaling received, or signal received from parent, it should have said. So yeah, this is the idea here is that with this wait call, the thread that calls it can kind of be efficiently put to sleep. And it can be woken up exactly when the signal is received, instead of having to kind of check constantly whether the signal bit is set, right? So this is kind of like a little functionality that the operating system gives us that makes life a little bit easier. The last thing I wanted to talk about with signals, which earlier above I had something like this. I said sc signal allow, and then I did full sig vector. There is a reason for this, and let me show you why. I'll comment that out for now, and what I'll do instead is, instead of having this while one, I'll just return proc es success. So now the child process just exits immediately, right? And we can leave this all here alone. Doesn't really change anything. Let's see what happens. We would think that we would get hello from parent and then just kind of wait forever because, you know, the child will never send this signal 5. So let's see what happens. So we actually get system exited with status 3, and 3 is the signal exit status, which means that the process received it means that the root process, the first user process, received a signal it could not handle. It was not allowed by the signal allow vector. And the reason why is because there is one special signal that is used by the operating system, and this is called fsig child. And what happens is that when a child process exits, automatically this signal is sent to the parent, always. And there's a reason why. Because when you spawn a child process, it is your responsibility to clean it up or to reap the process, right? So it would be nice if we could get a notification that says, hey, you spawned a child process and it exited. You should reap this now, and then you can return to whatever else you're doing, right? Now, the way we can do this, I mean, you could do this in many ways, but really what you use is the scproc reap function. And what this does is it cleans up the process you're reaping, and it gives you the exit code of the process to see, you know, how it exited. Did it error it out? Did it succeed? Stuff like that. So usually, I think the paradigm I was kind of going for was that you'd have something like this, and I'll call it the reaper. And what the reaper does is his whole purpose is just to sit around and wait for the sig child signal, and when it's received, it will call you know, the scproc reap function. So what would that look like? We could do something like this: FernOS error, and we could say, let's think about this. Let's do while one, and we could have error equals scproc reap. Also, if we reap with FOS max procs, it will reap any process, so any child process. And we will say null, and we could say proc exit status RCES and RCES. Okay, and we can say if error equals FOS success, which means we successfully reaped a process. We could say sc term put format s, and we could say reaped process with exit status %u. Actually, I'll do %x because that's what we were doing with previous process exit statuses. And we can print RCES, and then otherwise we can just go to sleep. So we could say se signal wait, and we're going to wait only on the child signal, and we don't need to know that. Okay, so now if we want to start our reaper, what can we do? First things first, we want to allow the child signal so that when someone does exit, it's no big deal. Actually, we'll just do full sig vector, so we can handle really any signal. And then we could say error equals sc thread spawn. So now this is kind of including what we did previously in the video with threads. We're going to give it the reaper. All right, let's think about this. And if this doesn't succeed, we'll just error out. So now, let's see what happens. Now, what we could do, in theory, is we could have our parent process doing some sort of work. You know, 25, sc term put s main, or yeah, parent main thread working. And then in here, maybe we could sleep for a little bit. So let's do 50. Let's think about this. So we would expect after a little bit, the child process would exit with the success code, and then the reaper would be woken up and print out that code saying, hey, I successfully reaped. So let's think. Did I miss anything? I don't think so. Let's see. Doing some work. Reaped process with exit status 0. Cool. So the reaper woke up, it reaped the process, got its exit status, which was success. Things are looking good. This can be useful in situations where the child process does something illegal. Like, for example, if we tried to write to Actually, let's keep this how this was. Controller. And let's do star uint 8t star ox0 equals 10. Now we're going to write to the null pointer, which should crash the child process. But because we're using luckily, because we're using processes, the entire system won't crash, and we should reap this process once it errors out. So let's see. Boom, boom, boom. Nice. So this time we got exit status 4, which means something went wrong. Well, if you made it this far, thank you very much. This project took a lot of work, and it's probably the hardest project I've ever made in my life. I actually took 6 weeks off work to make this, so I hope you enjoyed. Lastly, from here on out, I'll be contributing to the project using feature branching. So if you're interested in contributing to FernOS, you could. I'd be happy to review anyone's pull requests. So I'll put the link in the description. And with that, goodbye.